Okay, so today we are going to start talking about Laplace's equation. So there's two ways to think about where Laplace's equation comes from, and they're both kind of basically the same thing. So one is we can start with the diffusion equation, which says the t derivative of u is equal to the Laplacian of u. Now we have to be careful when I say, or sorry, not. The Laplacian of u. So I need to be careful. When I say the Laplacian of u, I don't mean in all variables. I mean in the x and y variables, and this is pretty typical. Often when we talk about like the Laplacian and the gradient, we mean we're only taking it in the space variables. Typically, if we say gradient or Laplacian, we don't mean we're taking it in the time variable. We typically only mean we're taking it the space variable. Okay, and so we've got the t derivative of u is equal to the Laplacian of u, and this just is, what this means is just the double x derivative of u plus the double y derivative of u. Now, if we imagine this modeling a diffusive process, as t goes to infinity, everything should kind of spread out and get stable. So as t goes to infinity, the t derivative of u should be equal to 0. That should go to 0. Okay, it's the long-term distribution of whatever we're modeling. It should not change. As t goes to infinity, it should stabilize. And so as t goes to infinity, that limit should go to 0. If this is equal to 0, the above equation is just as 0 is equal to the Laplacian, the x and y variables of u. Okay, so then the steady state solution to the diffusion equation is just going to be when the Laplacian of u is equal to 0. It's called the steady state. Okay, it's not changing, and so it doesn't depend on t. Even though these solutions depend on t, this doesn't depend on t. Now, if you look at what we've done so far, if you look at, for example, the diffusion equation on the real line, so we'll get to why we don't care about Laplacian on the real line in a minute. When you look at the diffusion equation on the real line, as we've seen, the only steady state solution for the problems we've seen are going to be solutions that are equal to 0. So this is not very exciting in that case. On the finite interval, it's different, and if you have different diffusive, if the material is different, it's also going to be different. At any rate, this is sort of conceptually what's happening. Another way to come up with this idea is to basically just say, all right, let's say u. So u models some concentration of something, and this is happening in the plane in R2. So u models the concentration of something. It could be heat, it could be dye, it could be whatever. And let's say F is the flux. And F is the flux. So if omega is we'll say a smooth, an open region connected, smooth boundary, so something like this. This is our omega. The flux, the net change, I should say, the net change in omega of u is going to be equal to minus the line integral oriented in the counterclockwise direction of the vector field, the flux field F, dotted with the normal vector. Okay, we talked about this in other times, but the flux vector, if this is the normal vector, the flux vector through this point might be something like that, but we only want the component that is parallel to the normal vector. That's what F dotted with N does. Well, by the divergence theorem, this is going to be equal to the double integral over omega of the gradient of f. Okay, now if we're in a steady state solution, so that there is no net change, like if we imagine a steady state distribution, nothing is moving at all, this net flux has to be equal to 0. And so since this is true over every omega, this tells us that the flux is identically equal to 0. Just using this fact that if we have a function whose integral is equal to 0 over every omega, over every open set like this, then the integrand must be equal to 0. So the gradient of f, or the divergence of f, must be equal to 0. Okay, now this is true, no matter what u is modeling. If u is in any sort of steady state configuration, it's going to tell us that the divergence of f is equal to 0. If in addition, really there should be a minus sign here, it doesn't matter because it's still 0. If in addition we know that u is a diffusive quantity, then what we can say is we can say that f is approximately equal to minus some function k times the gradient of u, and all of this becomes the gradient of k times the gradient of u, or the gradient dotted with k times the gradient of u. And okay, if this is true, if k is constant, then we can write this as k times the gradient, or the gradient vector dotted with the gradient u, but this is just the Laplacian. This is k times the Laplacian of u. Okay, and then again we have this is all equal to 0, so it just says the Laplacian of u is equal to 0. Okay, and so we get this equation here, but notice this is only in the space variables. I actually want to mention just a little bit about this kind of the notation with the gradient. This might be something that you're a little unfamiliar with. I want to just have our perspective changed just a little bit on what that symbol means. So a good way to think about that symbol is to just say, okay, this is a vector, and the length of the vector is going to depend on the number of dimensions, or the number of space dimensions. So if we're working in 2 space dimensions, we're going to think about this as being a vector whose first component is the differentiation with respect to x operator, and whose second component is the differentiation with respect to y operator. Okay, so then if we have a function, we think about this as a vector, and if we do gradient times u, think about this as being multiplication, where multiplication means do an operator. So if we just formally do this, if we just formally write out what this means, the gradient of u times this, well, it's going to be x, let me write it like this, times u. And what does it mean to multiply here? Well, we're just going to put, what does it mean to multiply a vector by something? You just put that something in the vector. If this something is a scalar. So we're going to have this, and then, okay, now when we say multiplication, like this is not literally like number-wise multiplication. The multiplication means we're going to do the x derivative of u and the y derivative of u. Okay, now if we have a vector field, this is a divergence operator. Let's say f is a vector field, we're going to put a dot there because we want to think about this as being a dot product. So the x derivative, or the gradient, is going to be the vector whose first component is the x derivative operator, whose second component is the y derivative operator. And then we're going to dot this with the vector field, and let's say the first component is f1, and the second component is f2. And when we do this dot product, we're going to get the x derivative of f1 times the y derivative of f2, and that's the divergence. This is just the divergence, right? Oops. Okay, so then what if we do this together? What if we do the gradient dotted with the gradient of u? Okay, well, it's going to be the gradient. The gradient of u is this. It's the x derivative of u, and then the y derivative of u. And then when I do the dot product here, well, actually, let me write out explicitly. This, again, we're thinking about this as a vector. The x derivative, the y derivative, dotted with the vector whose first component is the x derivative of u, and whose second component is the y derivative of u. And then, so what we're going to get overall is the x derivative of the x derivative. So it's going to be the x derivative of the x derivative of u plus the y derivative of the y derivative of u. And altogether, this is the double x derivative of u plus the double y derivative of u. And we call this the Laplacian of u. Okay, now one last thing to mention here is that we typically, instead of writing it like this, we write the following. So this is Laplace instead of writing the Laplacian of u equals 0, and this is true, no matter whether we're in 2, 3, 4, however many variables. A lot of times, instead of writing the Laplacian of u, we write minus Laplacian u equals 0. Obviously, mathematically, they're equivalent statements. If this is equal to 0, then that's going to be equal to 0. The reason that we do that, we'll see at some point. Minus Laplacian is what is called a positive operator, and we don't know what that means yet. It doesn't mean that it's always going to put out a positive number or something like that, but I'll explain what it is. Not in this video though. The Laplacian minus Laplacian. This right here, minus Laplacian is a positive operator, and then there is a non-homogeneous version of this called Poisson's equation, and it says it is minus Laplacian u equals f. And actually, we will use solutions to Laplace's equation to determine solutions to Poisson's equation. Okay, that's it for this video, introduction of Laplace transform. I think in the next video what I'm going to do is just show how we can use Fourier transforms to get something that seems like it should be a solution and is a solution to Laplace's equation.